Hi, welcome to Unit 4, Day 7. This is Structure of Covalent Molecules, and this video is Part 1, the Basics. The purpose of the Basics video is to provide you with the foundation that you need for Part 2 of this lesson, where you learn how to draw the Lewis dot structures of covalent molecules. Here's an outline of the Basics presentation. If you would like, you can pause the video to read through the outline. We're going to get started with covalent bonds review. Since we're talking about covalent molecules, it'll be helpful to review a bit about covalent bonds. But before we get into that, I just want to sort of remind you of what we've looked at in Day 6. In Day 6, we saw the 4 ways to represent molecules, and we focused on ionic compounds. And here's just sort of a quick reminder of what we did. If you want, you can pause the video and look this over. For ionics, we focus specifically on the chemical formula as its representation. So now let's look at the 4 ways to represent a molecule for covalent. So again, we have chemical name, chemical formula, structural formula, and model. So what does that look like for a covalent molecule? Well, if you look at the name, phosphorus trifluoride, in many ways it sounds similar to an ionic compound. A couple of key differences in the name. First off, it's a covalent molecule, so the atoms involved must be nonmetals only. Whereas in ionic, you have a metal and a nonmetal. So here, the phosphorus and the fluorine, they're both nonmetal atoms, so that way I know that it's a covalent molecule. The other major difference is the prefixes that go in the front, like tri or di or mono, etc. You do not find them in ionics, but they are present in covalent molecules. Next is the chemical formula. So the chemical formula for ionics and covalents look very similar. Again, the only difference is the types of atoms. So here we have both nonmetal atoms. And the chemical formula, of course, tells you the types of atoms you have. So we have phosphorus and we have fluorine and their ratio. Next, going into the structural formulas. First structural formula we're looking at is Lewis dot structure. And the Lewis dot structures show you the types of atoms that you have, how many of those atoms you have, and how they're connected. The Lewis dot structure for a covalent molecule looks very different from an ionic because the bonds are different. The next type of structural formula is the valence shell electron pair repulsion theory structure. And this structure is similar to the Lewis dot structure in that it shows you the number of atoms and how the atoms are connected. But it gives you a little bit more information because it gives you a sense of the 3-dimensional shape of the molecule. Whereas Lewis dot structures are 2-dimensional and flat, they don't give you that information. Finally, we have models like ball and stick model and particle diagram models. There's many different ways to model a molecule like PF3, and these are some very common ones that you may see. But this is just all to say that all of these are representations of the same molecule, and it can be represented in different ways and provide you with different pieces of information. We are going to focus for covalent molecules on Lewis dot structures in this lesson. So let's review how covalent bonds are formed since we're talking about covalent molecules. So remember, covalent molecules involve nonmetals, and they form bonds by sharing their valence electrons to get an octet. So here we have an example of a covalent molecule. Here's one atom, and here's another atom. And then in the middle here, I circled in yellow their bond, which involves 2 electrons that are shared between both atoms. The electrons are shown as the red dots. So one way that covalent bonds can form is by pairing unpaired electrons. So when I say unpaired, you have a single dot. It's not paired. Those are unpaired electrons that can pair up together to form this bond. And that's shown in this animation or movie GIF here. Okay. All right, so now we looked at forming covalent bonds, and yesterday we looked at forming ionic bonds. Let's see if we can compare sort of the key differences between an ionic bond and a covalent bond. So I want you to take a moment to read this CFU information, and when you are ready, fill in the blanks with the correct word. For example, in an ionic bond, electrons are what? Are they shared or transferred between atoms? And you'll do the same for a covalent bond. Pause the video now, and when you press play again, the answer will be revealed. Great, so in ionic bonds, as you can see in this movie, GIF here, the electrons are transferred from the metal to the nonmetal, but in a covalent it's shared. And that's the key difference in ionic and covalent bonds. All right, now we're going to go in interpreting Lewis dot structures in some key Lewis dot structure LDS terms. So let's begin by talking about what bonds are. Remember, bonds are the things that connect atoms and molecules. And in a covalent bond, as we mentioned before, it's electrons that are shared that make up the bond. Now, each bond will have 2 electrons, and they can be drawn as 2 dots or a line. So if you look at the images down at the bottom here, this is a fluorine molecule, or F2. In between the 2 fluorine atoms, you see 2 dots. Those 2 dots represent the fluorine-fluorine bond. And over here on the other side, it's the same molecule, except for instead of using 2 dots to show that bond, the bond's represented by a line. So one thing to keep in mind is when you're looking at a bond that's representing a line, remember that each bond has 2 electrons. So each line has 2 electrons. Now, you'll also notice that there's some other dots around here. These dots that are on the outside, so the bonds are what's in between atoms, but the other dots, they're known as lone pairs. And unlike bonds, the lone pairs are found on a single atom. They're not between atoms, but on a single atom. Okay, so let's see if we can use the information that we just learned. How many lone pairs does NH3 have? So here's your NH3 structure. Pause the video now. When you press play again, the answer will be revealed. Great, just 1. So the lone pair is this one here that's circled in red. And the reason why the answer is 1 is because even though there are 2 dots, just like if you have 2 sneakers, you would say it's a pair of sneakers. So a pair represents a grouping of 2. Now, if you chose the answer 4, your error here was that you were looking at bonds. Remember, the dots between 2 atoms, so between the nitrogen and the hydrogen atom, are bonds. All right, so these aren't lone pairs because they're between atoms. All right, how about diethyl ether? How many lone pairs does diethyl ether have? Pause the video now. When you press play again, the answer will be revealed. Great, it just has 2, and I circled them there on that oxygen. There are 2 pairs of dots, so 2 lone pairs. Now let's see if we can do something a little different here. This is the Lewis dot structure of diethyl ether. I want you to see if you can interpret use this Lewis dot structure to determine the formula for diethyl ether. What is the chemical formula of diethyl ether? Pause the video now. When you press play again, the answer will be revealed. All right, the answer is choice B. And the reason why it's choice B is because if you count up the number of carbons, you have 1, 2, 3, 4 carbons, so C4. If you count up all the hydrogens, you will count a total of 10, so H10. And there's only 1 oxygen, so we have O with an invisible 1 here. Remember, the subscripts tell you how many of each atom you have in the molecule. All right, some other key information that we need in order to interpret Lewis dot structures is the order of the bonds. So 2 atoms can be connected by more than just a single bond, as in the examples we've seen before. They all had just single bonds. So there are 3 different bond orders that exist. One is a single bond that we've been seeing, and where you have 1 line or a pair of dots between 2 atoms. And again, that represents a total of 2 electrons. You can also have a double bond. So double meaning 2. That means you have 2 bonds or 2 lines connecting the atoms, and that has a total of 4 electrons. Remember, each line has 2 electrons. So if you have a double bond, you have a total of 4. And a triple bond would have 6 electrons and 3 lines or bonds connecting the atom. Here are some examples of molecules with single, double, triple bonds. So H2, molecular hydrogen, has single bond between the 2 atoms. Molecular oxygen, the oxygen that we breathe in, has a double bond. And then nitrogen, which is the gas that makes the sky blue, has a triple bond. All right, so learning the bond order is important in order to describe a Lewis dot structure. So we're going to take a look at how we describe a bond like this, that's circled here. In order to describe a bond, you have to name the 2 atoms in the bond, and then name the order of the bond, so it's single, double, or triple. And I've listed the atoms at the top over here so it'll be easier. So in this case, I see I have a nitrogen and a carbon connected by a single bond. So I can call it a nitrogen-carbon single bond or carbon-nitrogen single bond. The order of the atoms typically doesn't matter. Let's look at another example. So for this bond, there are two carbons connected by a double bond, so I can just call it a carbon-carbon double bond. Even though they're both carbon atoms, you can't just say carbon double bond because we don't know what the other atom is unless you specify. So you have to say both. And then how about this bond? This bond has oxygen and a carbon connected by a double bond, so we would say oxygen-carbon double bond or carbon-oxygen double bond. All right, so let's see if you can describe the bond that's shown here. So pause the video now. When you press play again, the answer will be revealed. Great, this would be called a nitrogen-carbon double bond or carbon-nitrogen double bond. All right, how many carbon-oxygen single bonds does caffeine have? So this is the structure of caffeine. How many carbon-oxygen single bonds does it have? Pause the video now. When you press play again, the answer will be revealed. Answer is 0 because there are no carbon-oxygen single bonds. There are some carbon-oxygen double bonds. There's 2 lines there. So in order for it to be a single bond, it would have to just be 1 line between the carbon and oxygen. And we don't see that anywhere here. So the answer is choice A, 0. All right, next one is describe the circle bond in words, just like you've done before. So pause the video now. When you press play again, the answer will be revealed. Great, carbon-hydrogen single bond or hydrogen-carbon single bond is how you would describe that. Okay, last final thing on just getting used to structure is that for organic molecules, they're oftentimes really large, and so they abbreviate them. And the way that they abbreviate them is you have the structure here, you just see a bunch of lines and very few atoms, only oxygen. But each of the corners and ends of the line represents something. So each corner and end of the line is a carbon with enough carbon-hydrogen single bonds to give a carbon a total of 4 bonds. So here at this apex or this end of the line here, those are carbons. At the end of that line, there's carbons. And then we would just add enough hydrogens to give them a total of 4 bonds. So this is the structure of diethyl ether that you saw earlier before. Now, you don't have to know how to do it. You just need to know how to recognize it. When you see something like this, just know that there are carbons and hydrogens here. All right, now we're going to define what Lewis dot structures are. So again, we're focusing on Lewis dot structure just to remind you this is what they look like. So where did they come from? They were invented they were based on a theory invented by Gilbert Lewis, who was a professor at UC Berkeley. And his theory involved the idea that bonds were formed by pairing of electrons, which was something completely new and revolutionized our understanding of atoms and how they form bonds. And he was nominated 41 times for the Nobel Prize. He didn't win. However, he does have a building at UC Berkeley, if you ever visit, named after him in his honor. So this is Lewis Hall, it's the chemistry building at UC Berkeley. Now, what are Lewis dot structures? So they're representations of a molecule that shows the arrangement of valence electrons in a molecule. Remember, valence electrons are the electrons in the outermost shell, and each group has a certain number of valence electrons. In molecules, valence electrons can form either bonds, which connect atoms, or the lone pairs, those 2 dots. Now, remember, Lewis dot structures for ionic and covalent molecules are different. So ionics, you have these brackets and these charges, and you don't have lines to connect atoms, whereas in covalent molecules, you do. All right, so final thing, key reminders. You have to know valence electrons and electronegativity in order to do Lewis dot structures, and here's why. Starting with valence electrons, when you draw a Lewis dot structure, you need to count the total number of valence electrons. And in order to do that, you need to remember how to determine the number of valence electrons, which are determined by the group it's in. So if the element is in group 1, it has 1 valence electron. If it's in group 2, it has 2 valence electron. We skip the transition metals, and in group 13, it has 3, and so on. You also need to know electronegativity, and that's because the central atom, when you draw the Lewis dot structure, will be the least electronegative. So you have to sort of know the trends. Remember, electronegativity increases going to the right and decreases going down. All right, so the next video you're going to look at, or the next part of the lesson, is how to draw Lewis dot structures. Make sure you take notes on a separate piece of paper, and there will be practice there. You can choose to take pictures if you would like to show me for any help. But other than that, have a quality day.